So I wanted to wrap up 8.2 with just a couple of points that aren't necessarily on the quiz, but they're helpful later on down the road. And the first is just to make you aware of two theorems that exist, and they're used to establish that a sequence has a limit or in actually finding the limit. And the first one's the squeeze theorem, and you've seen the squeeze theorem before when we worked with limits of functions. And now we're using it with regards to sequences. And that's if you have three sequences and they are sandwiching one. So two sequences are sandwiching a third. Let me give you the order here. So these are three sequences, and B is the one that's sandwiched between A and C. And if A and C have the same limit, that is to say, if the limit as n approaches infinity of AN equals L, and also Cn equals L. If that sequence B is sandwiched between the two, then B also has the limit equaling L. All right, so this is the same theorem that you've seen before, but the squeeze theorem that apply for limits with regards to functions also applies to sequences. So that's the first one. The second theorem is called a bounded monotonic sequence theorem, and all that says is that if it's bounded and it's monotonic, then it's going to converge. So let me write that one down. So the second theorem just states if you got a sequence that's bounded, and this theorem is called the bounded monotonic sequence theorem. And again, all that it's saying is if a function's bounded, if a sequence bounded, if it's bounded and it's monotonic, then it's going to converge. All right, so a bounded monotonic sequence converges. So there are your two theorems that will help you establish that a sequence has a limit. The last point I want to bring up is really something that I already sent a video on, and that was growth rate of sequences. And this correlates directly back, just like the squeeze theorem does, to functions. Growth rates of sequences behave much like functions do. All right, and you can look back at the theorem in the chapter, but it looks exactly like the function theorem, except these are sequences. So, you should know by now that ln of, and you raise it to the cube power, right, of any, as n goes to infinity of any sequence, is going to grow slower, right, than a polynomial, which is going to grow slower than a polynomial times a log, which is going to grow slower than a polynomial raised to a higher level power, p plus 1, and what's changing here are the exponents, guys. Right? So just beware of what's changing here. And of course the exponential. Right, these are all series. I should have brackets around. These aren't functions, they're series now. Apologize for that. It's getting late. So a series involving exponentials is going to grow slower than a series involving factorials. And the king is the tower series, which is similar to the tower function. All right, so that's really a ranking. And it doesn't change if the sequence multiplied by a constant. Okay, this is exactly what you saw with functions. All right, so if you understood that, you should be able to substitute the sequences right in. The only thing that's different here that you didn't see in the function is the factorial sequence. But it's the same exact growth rate as functions. And that closes up 8.2. Alright, so this is the same as the growth rate of functions. Okay, and these last two subtle points are not explicitly on the quiz, so don't worry about it, but I want you to be aware of them for future material.